Okay, you can let go now if you want.
No, I want the rest of the class. The rest of the class.
So if you had a goal that was your body temperature, which is electrical.
I am.
What?
I know, I'm more likely to die. Well, because most heavy machinery is built for right-handed people, so me being left-handed puts me at a higher risk. That's an awesome stat. Oh no, that's gross. Rick, put it on the other side. Ugh.
Okay.
So,
Writing's not that easy, but Grammarly can help.
well, yeah.
This sentence is grammatically correct.
Today,
there's another amazing picture.
I should.
No, there is.
You sent.
Yeah.
Oh my gosh, let's see again.
So if your phone, you can't read.
Yeah,
Oh my
don't lose
gosh.
the privilege of retaking the unit test.
How dare you, Dan?
Frick, Winston's trying to get me to lose my retakes? What's the problem? Oh my gosh, Winston.
Trying to sabotage.
I see Winston.
Okay.
What do you?
If only this class was graded on a curve, that would be genius.
Okay. Now, what can sometimes seem surprising is that the literal temperature of the leg of your chair and the top of your table is about the same.
Whoa, rewind. What? It's like rewind 100.7.
Okay?
Wait.
So think about that as we watch kind of another example as he goes around and confuses more people.
That's my dad.
When you touch an object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book. And I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive?
The temperatures.
Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly colder than this one.
Yeah. Oh, that's warmer. Yeah, way more.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know if because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But
I
really?
think you're lying, yeah.
Oh, jeez. Well, maybe the way I can prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that, and I'm not a scientist.
Make a prediction for me.
I still think that's colder.
Would you bet me money?
I do it because I don't have any cash. So,
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. And measure the temperature of that.
19.0. Alright, well now I believe you.
I'm trying to actually figure it out, actually. Trying to figure out why they would be the same temperature. No, they don't feel the same temperature, though.
So why does that feel colder if they're basically the same temperature?
good on. Do you have an answer?
Well, I'm coming to you guys for answers.
We're creatives, not intellectuals.
Well, create an answer for me.
I'm not a scientist. Come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block and a plastic block. How do their temperatures compare?
Completely different. Completely different.
Much colder.
Yeah.
Yeah?
This actually feels colder.
Let's take this to the next level. I'm going to put an ice cube on both plates. What are we going to see?
Well, I'm guessing it would stay solid on this one and melt on this one.
So it's going to melt on the plastic but stay solid on the aluminium.
Yes, but maybe I'm wrong.
That one will melt more quickly than on the aluminium block.
Yes. I think so. I think they're colder.
Yeah, because it's cold.
Let's
I
actually...
think they're going to go the same.
All right, so we put an ice cube on each of those blocks.
Wow.
What are you seeing?
Well, it is melting a lot quicker on the aluminium.
I can't, it's melting.
It's melting quicker than that one, even though this is aluminium and that's plastic.
So which one felt colder?
That
This
one.
one.
How does that make any sense?
I have no idea, you know.
Could aluminium be bad for the environment?
How would aluminium be bad for the environment?
Well, it's thawing out the ice a lot quicker, isn't it?
So you want the answer?
Yes, please, please.
It's about thermal conductivity, right? The rate at which heat is transferred from one object to another. So when you felt these blocks originally, I know this one felt a lot colder.
Yeah.
But you know from the other example we did that they must both be at the same temperature. True. Because they've both been outside for a while. We see that the aluminium block is melting the ice faster than the plastic block because it's conducting the heat to the ice cube faster.
Okay.
With the plastic block, it's a worse thermal conductor, so heat is being transferred less quickly to this ice block, and so it's staying ice.
Okay. I believe you.
Make sense?
Yes. Definitely.
You know, in our first example, the hard drive felt colder even though it was at the same temperature roughly as the book. And that's because the aluminium conducts heat away from your hand faster than the book conducts heat away from your hand.
Sure, that seems logical.
Which makes the hard drive feel colder and the book feel warmer. So when you touch something, you don't actually feel temperature. You feel the rate at which heat is conducted either towards or away from you. Think about this next time you hop out of the shower in winter. It's much nicer to stand on the bath mat than on the tile beside it. Not because the bath mat is warmer, but because it conducts heat less quickly away from you.
Okay, so one thing that we need to establish in this unit, first off, is what he said there at the end, that when we touch things, we don't feel temperature. We're feeling the transfer of heat that might be happening, okay? So grab the leg of your chair again, everybody. You're not holding on to it still. Okay? How did the leg feel at first touch?
Oh, it's cold.
Typically it feels cold, right? Okay, now it's not actually cold, but the heat is traveling from your hand into the leg of the chair. Metals are very good heat suckers. Okay?
Yeah.
They suck the heat out of your hand so it feels cold to you. Versus the top of your table, which is not metal, the heat transfer doesn't happen as quickly, and so it doesn't feel as cold. On the reverse side, you've probably experienced this not fun example. Well, if you ever get into a car in the summertime and you touch the metal part of your seatbelt, right, when it's like 100 degrees outside, and it's like, yeah, you want to die?
Exactly like that. That's exactly what it is.
Arizona, it burned.
Yeah, especially if you're like in some, like when I go to Mesquite in the summertime, it's like,
You go to Mesquite in the
Wait,
summertime.
is that?
that's where my in-laws live.
Oh, that's such a pain.
Yeah, it's a hot place.
That's gotta suck.
Well, first time I ever went there, they had a whole week and it was 120 degrees.
Oh my god.
I don't know how people live in other places like
I
that.
think it's on the way to Vegas.
Yeah,
You
it's
always
like,
pass it when you go to Vegas.
yeah, right after you, have you ever driven to Vegas or California? Right after you get through the little mountain gorge, that little city's Mesquite. But once again, the difference here is when you touch the metal, right, it's transferring the heat very rapidly, versus if you touch the fabric of your seatbelt, it doesn't. So the other thing you have to be very cautious with in our lesson today is your perception. Okay, you can get every answer we talk about today backwards purely because you're looking at it on the wrong side. Because heat has to be conserved. The first law of thermodynamics, that first thing on your notes, is that energy cannot be created or destroyed. It just transfers to different places. Sorry, I'll get this pulled up here. And so because of that, if you look at it from the wrong side, you might be seeing the transfer of heat in the wrong direction, but you're not looking at it incorrectly. Okay? The two type of directional terms we're talking about today are reactions that are known as endothermic reactions and exothermic reactions. Endothermic reactions are the process where heat is entering the system. Think of endo as entering.
Endo.
Okay?
Or endo as you flip over and
That's true. Do you not know what
That's like when
No.
you crash, like generally biking.
Okay.
And you go over the bars and hurt yourself.
It's called an endo?
It's called an endo.
Really?
Yeah.
It's pretty fun.
It
You should
hurts.
try it sometime.
Actually, no. Sometimes it's really fun.
Yeah.
Like depending on the crash,
I
it
don't
can
believe
be
you.
it can be really fun.
Yeah,
It's true.
definitely. 100%. Just go down the street. All right. Just over
Put that on my to-do list.
I don't think she put it on her to-do list.
And then exothermic, think of exo as exiting, as heat is going out of the system. But once again, both have to be happening. Because if one thing is absorbing the heat, something else had to have lost the heat. So when we're focused, you always answer the question based on the system, not the surroundings. If you answer it based on the surroundings, you're always going to be backwards from what it should be. Evan.
So if energy can't be like created, where does it come? Or like, is there just a certain
The Big
amount
Bang,
in the
dude.
universe?
Yeah.
Oh.
So it can be conserved and transferred, so it can come out of things and go into things, but one of the fundamental things of science is they believe that all the energy that has been here is always been here.
Oh.
A lot of this is pretty good, but.
So, now one thing that you need to make sure is recognize that we, as humans ourselves, are not the system.
What?
Okay? So don't ever answer the question based on you, or if you are, it's always going to be opposite. Okay, so for example, when you're grabbing the leg of your chair and it feels cold, okay, if the chair is the system, we would say that this is a endothermic process. Because the heat is going into the chair.
That's why we.
Yes, so we feel cold because the system is taking our heat. Okay? Alright, let's keep going and we'll do a lot more examples as we go. Okay, endothermic reactions, once again, heat is entering the system. What that means is you're going to have a positive overall energy change. So when we start calculating energy change or heat change, the overall change in heat is going to be positive for endothermic because the heat is going in. What that results in, as we mentioned before, is a positive delta H. Now we'll talk a lot more about delta H as we get into calculations. The delta H represents the change in enthalpy, where enthalpy is the measurement of heat. Okay, once again, think of H as heat. Okay, when the energy change is positive, we classify that reaction as endothermic. Okay, in case you get it backwards, one way I think about it is like your bank account. Okay, where if your bank account is positive, is money going in or out of your bank account? It's going in. So a positive change in heat means energy is going in, endothermic.
Isn't it where like snow warms up the air? Because it like takes in the, or it, it's an exothermic reaction, so it gives the energy out into the air.
Whoa, 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 I never even thought about this before. Okay, wait, say that again.
So like, snow like being created is like an exothermic reaction, right?
So snow's a process, let's think about this. So snow is water freezing.
Yes.
Okay, so for something to freeze, is energy going into the water or out of the water?
Into the water. That was a joke, guys.
Big deal. Okay, so the energy's coming out to make it freeze.
So it gets warmer around
So
the
the air gets
So it
warmer.
gets warmer on the outside.
That's why the temperature raises when it snows.
So that's why it gets warmer when it snows versus when it's just like bitter cold, but there's no snow outside.
So it's
Wow.
like
Genius, Taylor.
caveman.
I never even thought about the connection before. Another way we'd see it, chemically speaking, circle this for me, everybody.
Now you're blowing everyone's mind.
Now everyone's just like, speaking about snow. So there's two ways to show heat in a chemical equation, okay? Sometimes they write it at the end, and then they just say delta H equals this. Other times they write it within the equation, like this, and they put it on a specific side of the arrow. When it's a reactant, that signifies that it's an endothermic process. So just a side note, remember kilojoules is a unit of energy. So if the energy is on the left side of the arrow, it's saying this is an endothermic process, you're putting the energy in. Or it's taking energy in from somewhere. Okay? Oh, let's draw. Another example is we could see them as graphs. So our energy profile graphs, these are our roller coaster graphs from last time. Okay? So for smiley face, I know there's not much space, it kind of got squished, so draw a little baby graph. Okay? Draw me a picture of what an endothermic graph would look like. And you can just do a one step, so it doesn't have to have like 2 steps. So an endothermic graph, what would it look like? Put your pencil down when you're done.
If this is the system, when you go up.
Yeah, boy.
Would it gain energy?
You know what? I'm just gonna go with you. Because
No,
you
but
tend
I'm not
to be
always
right.
right.
I
I've
know.
been wrong before. Don't go off of me.
Well, it's like
Okay, you have something like this, where you end
Yes!
up higher than you started. You can have some.
Dang it.
Get some.
Dang it.
You should have gone off of me, bro.
First, Winston tries to sabotage me.
Okay, now let's think of some
This
real life
day.
Everyone
examples
is against you.
Every world.
of endothermic processes we see in our life. Okay, so I'll start with one, kind of the opposite of what we did, but the process of melting would be classified as an endothermic process because in order to get the ice to melt, the heat has to go into the ice.
Not just milk sugar.
Okay, or melt sugar, same thing, right? Anyone else have another example of something that's endothermic in our life?
melting.
What about like when you bake something?
Warming up a hot dog.
Yeah, baking, cooking.
Okay, guys, I have a serious question. I know it doesn't sound serious, but so you go to a restaurant and you get a hot dog. It comes out hot. If I let it sit there for a while, does it become at some point just a dog because it has no temperature associated?
like that wasn't a serious.
No, I'm dead serious. This is all I've been thinking about all
Are you
day.
saying you call it a dog?
Yeah,
Room
what would you call
temperature
it?
dog.
Because it's not hot anymore. A lukewarm
Questions
dog?
of life.
This seriously has been haunting me all
They're
day.
always called hot dogs, even in this like freezer section.
Ah,
Like when you buy it at the store, the package doesn't say dogs.
okay.
That's like saying that when you bought it,
You know,
All of a sudden the label changes once they're heated up.
that's like
lethargy is a word. Like lethargic. Lethargy. I've been trying to figure out.
The act of being lethargic is lethargy.
You're asking the wrong teacher.
It's just that's also been floating around in my head today. And like, how do you use that in a
He just knows
sentence?
that you're so smart.
Right.
So
Yeah.
Right.
Bring
Uh,
back
Hot
these
dog
questions.
knowledge.
that's like calling it old orange like green. Like it just
Yeah.
That's a
Its
good
name
question.
is not
Is it
dependent
orange
upon-
that is not fully ripe? Green.
No.
You took
I mean, that was a really
away.
good example. I like that. Okay, coming back to endothermic or exothermic. Okay, the other thing I want to point out before you go to exo is keep in mind that there's always both, right? There's energy in and there's energy out. But we classify it based on the overall energy change. Did more energy go in or did more energy come out at the end? Okay, so let's look at exothermic in terms of chemical reactions.
Oh my gosh, microwaves are heroes. They're always giving and never getting. They don't ever expect anything, you know, in return. They're just always helping us. You know what I'm saying? Microwaves are heroes.
I was gonna say they are plugged in.
I know,
And
but
you have to pay like $50 or more. Somewhere around
you guys are trying to ruin microwaves for me. That's not gonna happen.
Okay, just let him believe that microwaves are heroes. Okay, few things here. Okay, so exothermic, obviously everything's in reverse. You're gonna have a negative enthalpy change. Once again, the negative is just indicating direction though. Okay, you can't have actual negative energy. It's just saying the direction of it. In terms of a chemical equation, notice the energy is now on the product side.
Whoa.
Okay, but notice that it's still plus. Okay, because there's no such thing as negative energy, but you can have a negative change in energy, just like you can have a negative bank account, but there's no such thing as negative money. Right, like I can't hand you a negative dollar bill. They don't exist. Right?
You can call it Apple Pay.
But it's not a tangible thing.
I think, isn't there like,
No.
yeah, that's it. Wait, if I wrote a negative number on a check, gave it to you, that means you owe me money. I should do this.
That's a good idea.
No, it's
You write reverse checks.
You can request
Oh.
digitally,
Yes.
which is like negative.
Yes.
Yeah.
That's true.
Wait,
That's true.
so could you like
Case
Venmo
study.
somebody negative money and then come into your account?
No.
That would be pretty awesome.
That would be
now.
so
You can,
cool.
yeah, you can request payments, but
Totally
you can't,
steal
yeah.
all their money.
You're all gonna try to go
Like
negative
$500
Necco everybody. New scheme.
Yeah, it's just Venmo.
Donate to the government.
Oh, that's true, yeah.
$4 million.
Ready? Here's what we're gonna do next. So I'm gonna show you 2 demonstrations. Okay. What I want you to try to connect once again with our chemistry triangle is what we're seeing with our eyes, and then what's happening at the molecular level. Okay. The objective with these 2 demos is to identify if it's an exothermic or an endothermic process in the end. Okay. You'll write these down in that. So this first little one, oh, I guess I have another little blank to fill in right there. Oh. Okay, we'll go to this and then I'll do it. Another type of process that we'll do pretty much in our lab is the process of dissolving or forming a solution. Okay? These ones can be endo or exo, as you'll see when we do our lab, so we'll kind of understand this a little bit more. But the basic idea here is you can simply dissolve a salt, so let's say NaCl, in water, and it can either raise or lower the temperature of the water.
Whoa.
Now, depending on the salt determines which direction it goes. In our lab we're going to do next week is the goal is to pick which salt would make the best hand warmer. Okay? But we could easily do a reverse lab and say which one would make the best ice pack.
Hand warmer, that
Hand warmer.
Whoa, wait.
just spun around, you held your hands around it.
That'd be cool.
You're gonna go far.
But this actually is how a lot of like quick hand warmers or cold packs work. Is there's liquid inside, there's a salt. When you hear that popping sound, you're mixing them together. And then that process of mixing causes an endothermic or exothermic reaction to create your ice or hot pack in the end. Now, what I want you to understand as we keep going though is this. When things come apart, it's always endothermic. I know this picture's not on your lab or on your notes, but the pulling apart of things is always endo. To break bonds takes energy. Formation of new relationships or new bonds is always exo. What determines the overall energy change is, well, how much did it cost versus how much did it release? Right, that's what determines if the overall is endo or exo. Okay, but one thing as we get into chemical reactions is we'll look at the bonds breaking compared to the bonds forming. And that's what will help us determine the overall energy change. Okay? Okay, so first reaction I'm going to do here is pretty simple. I have ammonium chloride, okay, and barium hydroxide. Here's your before picture for kind of what they look like. Pretty much I would describe them as salt and sugar.
Oh, cool.
Okay, that's how they look. Okay. All we're going to do is mix them together to cause a reaction to happen, and then we'll observe what we see. Now, after I do the reaction, I'll bring it around so you can get a closer look at a feel, because obviously we're dealing with temperature change, so heat has a key role.
What kind of wood is that?
I don't know my types of wood.
Is that pine? That
Solid.
doesn't look like pine.
Okay, what is going on?
Solid.
Is it soft or
That's
hardwood?
probably the best thing I ever did.
Well, there's probably soft and hardwood.
What kind of wood is that? Solid.
Okay, now, as I bring it around, and you react to what you see and feel, don't ruin the surprise for those that haven't yet. Meaning, don't announce what you notice. That make sense?
Yeah.
Let the people in the back experience it for themselves, people in the front.
I just experience it last so I can explain what I noticed.
Because you're gonna have a hard time keeping it in.
No,
Yeah, I think you should come over here, Lev.
Yeah, I think that's actually a good idea.
Wait, why do you need the board wet?
Is that like the baking soda?
Is
and
there
the,
water in
the
that,
other
or
thing, like,
was
mixing
there any
soda?
water?
No.
It's just
Yeah.
salt and sugar.
No, no,
That's
no, no.
it in that cup.
I mean, salt and sugar, yes.
Not actually, so I'm gonna go home and just get some salt.
Yeah,
and
you
sugar.
mix your salt and sugar. They look like salt and sugar, but they're not salt and sugar.
Do they
Wait,
taste
so
like
what
salt
are
and
these
sugar?
two barium chloride?
So it's barium hydroxide and ammonium chloride. two things I mixed.
So it's
Is it
two
gonna, like-
solids going into a liquid?
You tell me.
I don't know, you're closer.
Okay, I'll bring it around. Now the mask actually helped quite a bit, but it does produce a quite potent smelling gas.
All the cool.
If you'd like to smell it, you're welcome to take a waft of this, but don't get too close. Oh, what?
How is it?
That's why she got the board wet. It's probably
wanna feel
cold.
it.
That's
Well,
my
it's probably
guess.
frozen.
And it froze the water, yeah, so that's why it's sticking to it. That's my guess,
Oh.
guys.
You should
look at and see.
Gavin is so smart.
Yeah, I'm guessing it's cold and it froze the water. That's what it's
You'll know if you smell it. Uh-oh.
That's no dirt.
She like doesn't smell it. Like, I can't smell it.
Yeah, this would be our
Nice
COVID test.
Yeah, wait, I don't smell it.
I don't.
Here, let me taste a little. Nope, nothing.
Let me taste it.
Let me taste it.
Good idea.
That looks
Yo, Gabe, slap the board. See if it comes out. Wait, you gotta go to Taylor last. Skip Taylor. So then.
That's not fair. You're gonna explain more than me.
Wow!
Holy moly. Great googly moogly.
Oh wait, yeah.
Oh. Oh.
Honestly, it's not that bad.
It's not like stinky, it's just very chemically, it's very strong.
Are you gonna explain what it is?
You're feeling sleepy, this will like
It
wake you
smells
up.
like the sea.
No, what's it? Yeah.
You really couldn't?
I don't know.
Uh-oh. Okay, got it that time.
Oh, yeah.
You got it. Okay, so,
Did it freeze?
It smells like when you inhale water
this one's
through
more
your
salt than
nose.
nothing. Okay,
You know that feeling?
so there's our
Salt
ice
water.
ring,
I
that
was
was
right.
learned. So the board was just for demonstration purposes, you don't have to do it on a board, but obviously
But
just,
it's way cooler.
you
on
know.
board.
Haha, cooler.
Always think about that. So, okay, now here's the big question. Don't say it out loud. Don't say it out loud. But turn, oh, I'm getting
Yes.
whiffs of it. Turn to your neighbor and whisper with them, is this process we just observed endothermic or exothermic and why? Ready, set, go.
Oh wait, but that reaction. Oh,
That makes sense. This one.
Wait, are you talking about when it's happening or when we're touching?
Wait, Taylor, what'd you guys say?
Like when the two things are reacting together or when we're touching it?
So if there's still,
Like a good
that's a good question, Isaac, how do I phrase this? So there's still, like they're still reacting as I was bringing it around.
Okay, yes.
Does that answer your question?
I have to think about it.
Kinda?
It's not confusing me, I don't know why.
Okay,
You know when you think you're kind of smart and then you come to AP Chem and then you realize you're an idiot?
okay, ready? Here's your sign. Hey, but you're so much farther ahead than all the other people who aren't in this room.
That's true.
You're smart.
Did I ever tell you the one thing I learned with studying chemistry in college? Like my big takeaway was I know nothing. Every chemistry class I took in college just made me realize how much I don't know. Like, oh man, there's so much more I don't know.
Yeah.
So the more I learned, the more I realized I know nothing.
Yeah, that's what they say. Like learning something, you realize, you think you know it, and then you don't know, you realize you don't know it. And that's when you know it. I don't know. It's interesting.
Just make a t-shirt out of that.
Yeah.
Okay, you're gonna go like this if you think it's an exothermic. You're gonna go like this if you think it's endothermic.
Because that's kind of like an N.
I was thinking like an end zone.
Oh, she's a genius.
Okay, show me your vote. Endo or exo? Did I trick you?
Why are you guys doing this?
Don't look at each other, just show me your honest. So exo or endo? Which one do you think it is?
But it's cold, but that doesn't mean anything.
Wow. I tricked lots of last period, not on purpose. But you guys are alright, it is endo.
I totally would have chosen.
Okay, so just to make sure we understand,
Yeah.
how do I know that this process is endothermic? Someone if I raise a hand, help us out here. Claire?
it's taking energy away. That's why it's cold. So like when you're touching it, it's taking your energy to continue the process.
So if something feels cold to us, that's because the reaction is pulling heat from our hands into it.
I told you.
And like the water
No, you agreed
flows.
with me.
Good. Or you can look at the water, right? That it pulled the heat from the water, which caused it to freeze.
But I
Now,
was right.
where a lot of students last year got mixed up is they just focused on the wrong side and they looked at it from like the water's perspective. Water freezing is freezing endo or exo. Exo, right? Because the heat is leaving. So that's where you just got to be so careful with your perspective, because otherwise you can backwards. Okay. Okay. Second demo. Oh yes.
Oh, sorry, I have a question.
You're good.
So I'm getting confused with the graph here because like if we make something new, you said it was exo, and that was showing like signs of a chemical change, which would be creating something new, right?
Let me maybe clarify that. So endo and exo will create new substances.
Okay.
What happens here is it's just a balance of it takes energy to pull things apart, and then when things come together, they release energy. So in this example, because it's endothermic, it takes more energy to break the bonds than it does to form the new ones. Does that clarify your confusion?
I forgot we had to add the differences.
Oh, okay. No, good clarification. Okay, second demo, we gotta go into the lab.
Let's go! Hey, Prince. Hey, Prince.
Isaac, can you stop that? Thanks, Gabe.
Let's go, Gabe.
Okay. So the reaction we're doing is a reaction of sugar.
Is it real sugar though, or is it fake sugar?
She's lying. It's not sugar.
In the words
No,
of
actually real sugar.
Let's go!
And potassium chlorate.
So banana.
Okay?
Banana in a pool.
Now, there's a pre-step I'm going to do to help this reaction go faster, because we like things to go faster. Remind us, what are some things I can do to make a reaction go faster?
catalyst,
Okay, what else?
heat,
Temperature, what else?
That's all.
yeah, surface
Hello,
area.
positive things.
And current. Concentration, what else? I haven't heard the one I'm looking for. Movement-ish.
Temperature. What the heck?
Spreading them out.
Oh,
So surface area.
yeah, she said that right here. It was
I
really,
didn't hear Skyly.
it was really
Okay,
quiet.
so surface area is another way. So right now our potassium chloride is a solid, so I'm going to melt it, break it down to help it react. But this is not the reaction, okay? Once it melts, I'm going to turn the heat off, and then we'll add our sugar, and the form of sugar I'm using is in the form of a gummy bear.
Can I eat all the other?
The gummy bears are pretty much like
I love them.
straight up sugar, right?
Yeah, they are.
Okay.
Wait,
That's true.
you should demonstrate to us that the straight up sugar by giving me
Yeah, I
one.
think it's just like.
You know, I don't know if I can believe you unless I taste it for myself.
You want to taste one of these gummy bears?
Yeah, well, I've seen a guy put out a match by just eating it. So I think
Have
we
you-
should do that.
Could you imagine with my mask on and light my mask on
Have you
fire?
ever just done this too? Like,
So
that.
Taylor, I don't know when I bought these.
oh, I see.
Yeah,
okay.
I'll still eat one though.
In exchange for
Listen,
smiley
ready?
face.
Gummy bears to drop like
They're pretty darn hard. Like you might lose
Gummy
two
bears
on
to
it.
drop
You just have to suck on it.
Because I bought these for the purpose of this demo. I mean, probably when Skyridge opened. And then I
That's
just
4 years. I can
keep
take
them in the
one.
cupboard and then pull them out every year when I need them. So.
Wait, so what about the Skittles? How old are those Skittles?
Those aren't as old.
Oh, let's see.
I'm like a year old.
Maybe give you one of those. But. Okay, sorry. This is not the exciting part.
That Sour Patch
I'm
Kids, like
excited.
a bunch in the container. I was so sad I didn't weigh in.
Yeah, those are just the leftovers from that.
So sad. The Sour Patch Kids are
Did you go steal more smiley faces on the wall that you
Oh, what are you talking
No,
about?
what?
Oh my!
Who would do that? Who likes smiley faces?
All this my faces.
I'm gonna just collect them now.
Gavin's starting a black market.
He's gonna open up his jacket.
10 cents for a, 10 cents for a smiley face.
I think we should turn these in for smiley faces.
I feel like it's not fair now though, because you got a head start.
You did.
I can put him back.
Yeah, Gavin will
I
put
can
him back.
If this is a thing, I will gladly put him back. To
Just
start
take him back
fresh
down.
for everybody.
That's why I'm going like, I'll check and be like, you know,
I just told
on
him we'll clean 'em up.
B7 on Friday, they might all disappear.
Yeah, that's true. That's awesome.
Okay, sorry, this is not the exciting part. I should have
I
said.
think you should do some stand-up real quick.
I am standing up.
Oh, that's a good one. Keep going. Keep going.
That's all.
That actually was pretty funny though.
Oh. Yo, Max, I saw that video that dance you did in that one class. You know what I'm talking about? You dressed up for it or whatever.
Wait, like
Student council.
Oh, the Napoleon Dynamite one? Wait, when was this?
Do it.
Wait, was it in 7th grade?
Yes.
That was so
Wait, are we talking about 7th grade?
Yo.
No, this just barely.
Yo, McKenna Taylor totally showed it to me, and I was dying. I was like, what the heck?
Dude, this is what I've learned. If you have a terrible paper, you might as well give a really good presentation.
Did it
And
work?
I got like an A-, so.
That's pretty good.
It works.
Hey, just do an awesome dance.
But what class was that for?
It was for, it's like student council, but it's
Oh,
like
okay.
concurrent
I
enrollment.
thought, yeah, okay.
I don't know what it's.
Concurrent enrollment student council?
It's
I know,
like,
it's just like,
it's
what?
kinda weird.
Okay, so it's like
You have to take
solid,
these tests.
it's at Solid Community College, and then it's like leadership.
Oh, the leadership principles?
Oh.
Oh, that's cool.
Yeah,
So
so
it's
you,
like credit
oh,
for it.
we have to do
Touching
assignments and
assignments.
stuff.
I know, I thought it was too.
That's so cool though.
Do you want one? Oh, no.
Hey Gavin, you got the smileys.
Hey, don't take these. Good. No.
Okay, or the other thing that you can do with smileys here, I'll demonstrate it. I'm trying to start this, okay? What you do is you take the smiley, you rip it right above the smiley, okay? You turn it around, okay? And then you tape it
Oh, wait.
and connect it to the wall. And
Turn
now,
all the happy
yeah,
faces into
happy
faces.
face. Okay, if you look, frowny face. It used to be a smiley face, right there. Okay. If you come to school, this is your job.
These are the at-home students.
Don't you know that song like turn your what's that?
Turn that frown upside down.
Turn that smile into.
You're in the wrong direction.
I don't know. I heard smiling is like pointless or something, so.
I read this article that said, smiling is
Don't
where-
quote Gavin. Okay, here we go. Ready?
I say some wise things. every
Okay,
once in a
so the
while.
heat is off, so now the reaction is between this and that.
Oh.
Okay?
Wait, what is that?
There was
Oh, it's a
like
gummy bear.
Socrates one day.
Oh.
Oh my gosh, you sound like a monster in Minecraft. Like,
Wait, which monster?
I don't know, drown. Is this how rockets
Supposed to
work?
jump out.
That's how I want to be executed.
Just pour a ton of sugar on you, dump you in a solution of
We'll need all your stock.
something potassium chloride.
Get back in there.
Doesn't that
Normally
sound like a
doesn't
drown?
jump so much. I think I'm being harder.
Yeah, it does.
We might need to do another one.
Wait, if you like slice them up a little bit, would that make this reaction go even faster?
Yeah.
That's
Or if you did just
straight up. You're just making bugs out.
Is that some of the other ones?
Is this on the
So
yeah,
I melt a banana and throw some gummy bears in there.
No, you have to melt some sugar too.
Really? Oh yeah, but I thought that was just the gummy bear was the sugar. Isn't
Yeah, so
that
the-
banana in there?
Yes.
Yeah.
Melted banana.
So if I get a banana, melt it with some chlorine, and then throw some gummy bears, they'll just start popping.
Oh, that one's pretty.
Yeah,
Oh, that's so stuck.
that's okay.
You can burn it off.
Yeah, smoke them out of there. Oh my gosh, you pulled out his like freaking spinal cord.
Okay, that might be all we get. It got really stuck in
Smells like
this.
s'mores.
It's not basic idea. What else can I cook?
Yeah,
Like 2 minutes.
yeah, just give it a minute.
Wait, hold it with the thing.
What? That's gonna hurt your, yeah.
Okay.
How is she even gonna aim that though? That's like impossible.
Oh.
Oh my gosh.
I might have used up all.
It's like
Oh my
it's
gosh,
fingers.
it's so sticky in there. Ah!
That's so evil. What have you done? Harold!
I don't think we can get Harold.
You don't name your gummy bears.
Yeah, I think it's done.
I name them and eat them
We
one
said a
by one,
basic idea
saying
before
sorry.
the giant.
Do you have to clean those?
Sorry, Harold.
Sorry.
Do I what?
Do you have to clean those?
That?
Yeah.
I'm gonna throw it away.
Okay, good.
Yeah, this is one of those demos where cleaning it's not worth it. So, okay, back into the classroom. Let's talk about it.
Alright. Go.
Say we get home. When you do that,
It's for a blue, but blue are rarity. I need blue for a blue.
Yeah, one of my sounds weird, but like one of my dreams I've had as a chemistry teacher is to do that experiment with one of those giant gummy bears.
Oh. We should go outside and do that.
I'll buy the gummy
It definitely would have to be outside.
You'll buy the
How
gummy bear?
expensive is one of these gummy bears?
Yo, we can make a cannon.
Oh.
I've never seen like a gummy shark before, like those like $10 gummy sharks that are like.
Yes, if we were to do it, doing it now in the snow would probably be the safest time.
That's true. Get on it. Get on it, Kimberly.
Welcome back to something.
Let's do it like.
I'll pitch in
The melted.
I'll pitch in $5.
How much does gummy bears cost?
If they're really expensive, I'll pitch in.
Think about how, sometimes it's like, what container would I do it in? It would take the bucket, I class period to just melt. Yeah, it would take a long time to melt powder.
Not happy. Getting too
And start melting. Like, that's what would I melt it in?
melted on the hood.
Or I get a person
Home Depot. I can't put fire under Home Depot bucket.
leave that in a car.
Okay, focus back up right here. We'll ponder that idea. Keep going.
Okay, I can put them back.
Oh,
So
I
you'll
know.
start.
We just have to go to like, do you need to stay when they're like lava buckets?
No, I will. I'll just put them in a place where they can. Or I guess put it
Place
back.
on top.
When they zoom in.
And then like keep it on the bottom, and so it just like holds all the sugar in the bottom, and then you can actually like melt it in.
I'm not sure about that. Okay, so, yes, Isaac.
I have a question. On the satellites, is the telescopes on it, or like where they zoom in, are those good enough to like see molecules or something like that? Because they have to zoom in a lot to see like trees and stuff. So like if there's something right next to it, to see molecules.
Oh, I don't know.
It'd probably be
Well, I would say no, they can, because that just shows you the perception of how small molecules are still. So that is a really interesting question of like how small can they, like what size do they see down to if it's not focused in on a certain point, you know what I mean? So, I don't know.
Cameras or
That's a
what
good
cameras
question.
can see?
I was just thinking, like, could you power a car with gummy bears?
You can use potatoes.
Those like little explosions, right?
Yeah, I guess theoretically,
Gummy bear
It
car.
wouldn't last very long.
Gummy bear.
because you just need a combustion, right? And so that's a combustion reaction.
You would use a lot of gummy bears.
You just like dump sugar into
No.
What is the most efficient gummy bear?
There'd probably be a million gummy bears.
Yeah.
Yeah, but they just those cylinders have to fire so fast, so you need like so
Yeah, I don't know if it'd be like worth it, but could you?
Yes.
Theoretically.
Okay, now, as we talk about heat transfer, everybody, another important thing to understand is this idea of how things can come to a state of equilibrium because heat gets transferred. Okay, simple example, if you take a cup of hot water and I take a cup of cold water and I mix them together, eventually it all becomes one temperature as it reaches this state of equilibrium. So the molecules, if you imagine once again, this is your cold thing okay, they're bouncing around. When they come together, as they collide, they transfer heat, and then they reach a state of equilibrium. Now, keep in mind, this only refers to things that are literally at this different temperatures. You can kind of make a similar idea, though, to like when you grab the leg of your chair and you keep your hand there long enough, it doesn't feel cold anymore, right? Because it gets to a point where it equals out, okay? Energy always flows from high to low, or heat always flows from hot to cold. If they're equal, heat doesn't flow anywhere, or energy doesn't flow anywhere, okay? So what we're going to do before we leave is introduce, we're not going to get into it all the way, but, oh, I guess there's some more blanks to fill in, how we can calculate experimentally actual heat change. So not just understanding and labeling things as exo or endo, but if I wanted to, I guess for your question, Kimberly, if I wanted to figure out, okay, well, how much heat is that producing, or how much energy, could I use that energy then for something else, is known through an experimental study called calorimetry. Calorimetry is the study of heat or energy. Calories is what we deem as a unit of energy for food.
Yeah.
Right? That's where it gets its name of calorimetry. But once again, calories is just a unit of energy, just like a kilojoule. Yeah, Matt?
So, how complex of a sugar would it take to make that reaction that we did with the gummy bear? Like, would it be like, does it have to be a simple sugar like the ones in the gummy bear, or like, could it be a less complex?
Would a starch be like more effective? Because like a starch is just a bunch of sugars clinged onto each other, right?
Yeah, so I'm making my
would a
gummy bear
starch
car.
be more effective?
I'm not positive, but I believe, yeah, because it's mostly just a combustion reaction, so any hydrocarbon should work.
Or what would work best?
You know, if I ever meet Neil deGrasse Tyson, I will ask him if I can make a gummy bear car.
I don't know.
You don't know who Neil deGrasse Tyson is?
Because Taylor, I don't know if there's a straight up connection between energy. I'd have to look at like combustion reactions, and if there is a direct trend between, I would assume, once again, I don't know, this is just an assumption from Miss Alviso, that the simpler it is, the more energy it would put out.
Yeah.
Because then there's less bonds to break, because breaking bonds takes energy, right?
Yes.
But I also don't know, because the bigger it is, you would be forming more bonds too. I don't know. I'm not positive. Yeah, Max.
So if we did the same experiment where we had the gummy bear and then we had another tube with the same stuff in the bottom, and then we
Yeah.
brought the blueberry in, would it have a less, I guess like a small reaction then?
I would predict yes. Mostly because the blueberry has a lot more other things in there, like the grams per sugar are less in a blueberry versus a gram of like how many grams of sugar in them. But I don't know. I'm gonna bring a blueberry next time. We'll try it.
Just one.
Wait, really?
What if I brought like a gallon of sugar and then we dumped it in with like a gallon of potassium chloride?
That's the same
I'm
idea as
counting on you
giant
to do that. Yeah, but the sugar is more effective because the gummy bear
Doesn't
has
have all the
little
filler
things.
stuff. Yeah.
Can you increase the surface area of the giant gummy bear as well?
Oh,
Oh, just cut it into sheets.
so you like flaming
Or
gummy
just
bear.
use
What would we put it in to make it do
We're
this?
visualizing like an
I'm
erupting
gonna
volcano of gummy
I know, at that point, just use a gummy bear.
We would need at least like a metal thing because how much pressure would I build? It would just destroy
Yeah,
it.
but also, it's just glass shards.
We should just like,
What if you like put like
not have it locked
stars?
up, have it kind of use like, so then it'll go like that and it'll lift it.
Yeah, that's what you kind of see. You could just use.
It would not go flying like a gummy bear.
Open,
But it would go very quickly.
open field that has snow. Yeah, with flash, so it,
What do you mean?
So it's more consistent. You either have to go through the hole or
For the
the
mustache.
plastic.
Okay, I got this.
Okay, last equation I want to introduce you you guys to before next time, okay?
Sounds like it'll start.
Q is heat. Okay, so this is how we can mathematically calculate from an experiment how much heat in terms of a number is being released or absorbed. Okay, M is the mass, because obviously, like we're talking right now, how much of a sample you use will determine how much heat can be produced. Right, a bigger gummy bear will produce more heat. Okay, C is the specific heat. Now the specific heat refers to a pre-calculated value that is take into account the influence or how much heat a substance needs to raise in temperature. Okay, so the unit for specific heat is joules per gram, and then it's either in Kelvin or Celsius. What this means is it says how much heat is needed to raise a substance by 1 degree. Okay, so for example, water has a specific heat, and I think I have a table down at the bottom of a bunch of them. But water has a specific heat of 4.18. What that means for water is that it takes 4.18 joules to raise 1 gram of water up by 1 degree.
Whoa.
Okay? Because not everything changes heat the same. Honestly, water has a pretty high specific heat compared to most things. It takes a lot of energy to raise its temperature. A lot of metals have very low specific heats because it doesn't take very much for them to heat up. Right? You don't have to put as much energy in to heat them
So
up.
like, while metal might have a higher melting point, it gets there faster? Is that like a good way to put it?
I guess you could kind of think of it that in compared to like,
In water.
Yeah.
Like water.
yeah, like in, kind of interesting to think about it as a rate thing, but yes,
Okay, that's a good way to think about it.
because it changes heat very quickly,
Yes.
but you have to get it really, really high to get it to melt.
Yes.
You know, water doesn't have to get as high to melt, but it does take a lot to get it to melt.
That makes sense. Alright, thank you.
Yeah, that works.
Oh, yeah.
Oh, and then this is change in temperature.
Where is melted water? Water is.
Okay, so these are experimental values that we control in the lab, and then mathematically we can determine how much heat was released. Now to perform a calorimetry experiment, you'll use a calorimeter, is the device that we use. They're very expensive technical devices that look like this.
I really went, oh, I was gonna say, please don't let me have that.
But really, like, this is actually a calorimeter. Now, I know you're like, that's not very impressive, but look.
I eat snow cones out of there.
Two of them.
Oh my gosh, oh, that's
That
it.
is too far.
It's like magic stuff.
That is disgraceful.
But pretty much all we need for a calorimeter is a device that controls heat. Meaning heat can't come out and heat can't go in, and styrofoam is a good insulator.
That's true.
Now, it's not perfect, and we'll talk about that error factor when we do our lab, but it actually does these do a really good job. There are other types of calorimeters out there that obviously are controlled in other ways, particularly if you're doing a reaction that involves an explosion. Because you don't really want to do an explosion inside a styrofoam cup. I don't want to do an explosion in a styrofoam cup.
Wait, what is it?
So they have these other ones that are called bomb calorimeters that are for that. Yeah, they're called bomb calorimeters because they're literally like you're doing a little explosion inside of them, right?
So is a cooler
What's the point of making a
calculator?
bomb if you're doing it inside
Say that
of a
again,
calorimeter?
Is a cooler
You know what I'm saying?
or something like that?
Yeah, so in a sense it could work the same because you just need something that insulates. Yeah. And coolers work the same way where they keep the cold. Okay.
Dude, the smell of that thing is still like in my nose. Yeah.
That just means you don't
Okay, you got 4 minutes.
Yes.
Trying to solve this problem?
I'm gonna draw one.
Okay, we're gonna pause here because I don't want to get halfway through the problem and the bell ring. So someone remind me we need to start by solving this.
Alright, 6.48.
Okay? Now, what I decided, and I already decided this last period, but your homework tonight, if you've looked online, it says to do worksheet 6.4. We're gonna hold off on 6.4 until we go a little bit more in class. So you don't need to do 6.4 quiz either tonight.
Yay.
So you do need to do 6.1, 6.2, and 6.3, but you don't need to do 6.4. Okay, and then the big one is though, before you do any of this, is take Unit 5 test.